Okay. Our goal today is to find some atomic masses. Okay. So somebody asked you to define atomic mass. Just look at the name. What would you say? The mass of an atom. Okay? So that's a pretty good definition, except that you run into a couple of problems when you try to do that. Okay? First problem, you try to answer a question like, how heavy is an oxygen atom? Okay. You go to answer that question, you run into a problem and that it's a trick question. Because what we learned about on Thursday and Friday was there's more than one kind of oxygen atom. All oxygen atoms have to have 8 protons, but there are some with 8 neutrons, oxygen 16, some with 9 neutrons, oxygen 17, and some with 10 neutrons, oxygen 18. There's more than one kind of oxygen atom. So it's kind of a trick question when I ask you, well, how heavy is a car? Well, if you're building a bridge, that's an important thing to know, right? How heavy the cars are driving over the top of it. But do you think they take the time to calculate every potential car as it crosses that bridge? They end up talking about the average car, right? Well, same thing here. We're never going to have just one oxygen atom. We'll always have a bunch of oxygen atoms. So we're not concerned about the individual atoms of oxygen. We're concerned about the average oxygen atom. Bless you. Just like on the bell work, none of the rocks weighed 52 grams, but the average rock weighed 52. So the average atomic mass is not what any of the pieces weigh, it's what the average one weighs. Now, occasionally, when I assign that bell work question, I get people who give me the answer 55. But the average rock weighs 55 because you got 50s and you got 60s, and halfway in between is 55. Why didn't we just say 55? Why isn't 55 what the average rock weighed on the bell work? Why wasn't the average rock 55? Instead, we got 52. Why was the average rock lighter than what the average rock would be? No idea. There was, it's really basic. There was more of the things that weighed 50 than weighed 60. So the average should be closer to 50 than to 60. So you got to take into account not just how many different types there are, but how many of each type there is. So I have to take into account abundance. Abundance means how many of them there are. So to get my average for 52, I had to take into account that there was more of the 50 gram rocks than there were of the 60 gram rocks. Because the average is closer to the one you have more of. Okay, so that's our first problem. Somehow we're going to have to deal with the average one. Second issue. I hate to bring up my problems, but our second issue is, do we want to write these answers down in grams? I mean, the answer in grams is like, well, they said a hydrogen weighed like 1.67 times 10 to the negative 28th kilograms. Do you want to do math of 1.67 times 10 to the negative 28th kilograms? Nope. Neither do scientists. Scientists are lazy too. They're going to find some shorter way than have to deal with this all the time. So we can't use grams because the numbers would be way too small to be convenient to work with. Everybody okay with that? So I need a new unit. Okay, so I need a unit for mass. I don't want to use grams. Because I don't like dealing with numbers times 10 to the negative 27. Okay? So, to measure atomic mass, they had to come up with a new unit for atomic mass. They were very creative in its name. The unit they use for measuring atomic mass is called the atomic mass unit. Let's go with the obvious. What are you going to call a unit that you measure atomic mass with? We will call them atomic mass units. And the nobody ever writes out atomic mass unit except the first time. The abbreviation is AMU. So AMU is like grams, only really, really small. So they had to pick something that they wanted to use as a unit. Okay? And they were very specific about what they picked. They picked 1/12 the mass of a carbon-12 atom. So you take a carbon-12 atom, take its mass, and divide it by 12. And that's 1 AMU. There had to be a reason why they picked carbon-12. Because they had to pick something. Fact is, chemists picked carbon-12. Physicists picked oxygen-16. Okay? And actually, we had two different periodic tables for a long time. One for chemists, one for physicists. Okay? So there had to be a reason why chemists picked this one and the reason why physicists picked the other one. Well, let's look at carbon-12. Okay, carbon-12's got three kinds of pieces: protons, neutrons, and electrons. Which ones do I have to worry about when I'm talking about how heavy it is? Protons and neutrons, right? So how many protons are there? Well, it's carbon. Carbon's number 6, so it's got 6 protons. So carbon-12 would have how many neutrons? 6. Okay, they picked it because it had an even number of protons and neutrons. They also picked it because it's really abundant. Because I'm going to take the weight of 6 protons and the weight of 6 neutrons and divide it by 12. Well, first of all, we said protons and neutrons weighed almost identical, right? So I got 12 heavy pieces, I divide by 12. That tells me how heavy one piece is. That each AMU is about 1 proton or 1 neutron. It's a little bit off. Each proton, each neutron is about 1 AMU. It's off for a couple of reasons. One of them is we're not talking about the electrons. And the other one is we've got some mass changes that go on when we put it together. Now, each isotope has its own atomic mass. Because it's got its own mass number. So if carbon-12 weighs 12 AMUs, how much would you expect carbon-13 to weigh? 13 AMUs. It's going to be pretty close to that. Uranium-238? 238 AMUs. Because if each proton or neutron is about 1 AMU, your mass number is your AMUs, or pretty close to it. So now we can weigh the atoms. We got a unit for it. Now we just need to take into account how many of each kind we have. Okay, with the rocks, you had 4 and 1. You could either just add them up and then divide by 5, or you could do some fancier math. But what I want to show you now is I want to prove to you that you can use percentages to find averages. Okay? Because it's how I calculate your grade. Would you like to know the math behind how I calculate your grade? Well, what do I do when I say 40% of your grade is tests? What do I deal with that number? Okay? So this next thing is we're just going to work the bell work out. And I'm going to work the bell work out to the point where you can do it by percents. Okay? So this is the bell work question. Hey, it was Johnny, not you, but Johnny has 5 rocks. 4 with a mass of 50 and 1 with a mass of 60. What is the average mass of the rocks? Okay, we all know the answer is 52 because we did it for bell work. Okay, first you had to total up how much the rocks weighed. So the total, I didn't add, I did 4 times 50 plus 1 times 60. Did we look at that? 4 times 50 is 200, plus 60 is 260, the total is 260. And then I took that total mass, and in order to find the average, I divided by 5. And I got 52. Everybody okay with that? Okay, now I'm going to take this, and I'm not going to do, all I'm going to do is some simple algebra steps and show you how you could have done it with percents instead of 4 and 5, or 4 and 1. Okay, first I'm going to do the opposite of what you usually do with fractions. Usually you work really hard to get the same denominator so that you can put the numerator together. Well, I'm just going to take this one where they both have the same denominator and separate them. So I'm going to break this in half, and 4 times 50 over 5 plus 1 times 60 over 5 is 4 plus 50 times 1 plus 60, or plus 1 times 60 over 5. Everybody see that's all I did was just take that plus sign and make it into 2 fractions. Is that okay to do? Well, actually, we can check because it's supposed to equal 52, right? 4 times 50 is 200, divided by 5 is 40. 1 times 60 is 60, divided by 5 is 12. 40 and 12 makes 52. I'm doing the same math. You okay with this so far? Now I'm going to do is regroup. And instead of the 5 being underneath everything, I want the 5 underneath the 4 and the 5 underneath the 1 and turn them into fractions. So 4/5 of 50. Well, 4/5 of 50 is 40. Plus 1/5 of 60. 1/5 of 60 is 12. 40 plus 12, we're still at 52. I'm not doing, it's all the same math. Now I'm going to take that 4/5 and turn it into a decimal point. So 4/5 is 0.8. 1/5 is 0.2. Okay. Everybody, and 0.8 times 50 is 40. 0.2 times 60 is 12. We're still at 52. Okay, so now we're ready for percentages. 4 out of 5 of my rocks weighed 50 grams. What percent was that? 4 out of 5? That's 80%, isn't it? So 80% of the rocks weighed 50 grams and 20% weighed 60 grams. Well, 80% means 80 over 100. That's 0.8. 20% means 20 per 100, 20 over 100. That's at 0.2. So what we're getting to is, in order to find the average, all I have to do is take that percent and turn it into a decimal point and multiply by that piece. And take the other percent and turn it into a decimal point by moving it over twice. and multiply by that piece. And then add those two pieces together. Or I could write it as, to find the average, take the percent as a decimal, that 0.8, times the mass, plus the percent as a decimal, times the mass. So that's a percent of decimal of the first one, times the mass of the first one, percent of decimal of the second one, times the mass of the second one, percent is the decimal of the third one, times the mass of the third one. When do I stop adding? When I run out of different types. If there's 3 different types, I'll have 3 percentages. I'll have to add up 3 things. Here I only had 2 different types, so I had 2 things I had to add. Okay with that? So that's the math we're going to do today. We're going to find out how much the average was. So, let's try one. Calculate the atomic mass of copper if copper has 2 isotopes. 69.11% has a mass of 62.93 AMUs, and the rest has a mass of 64.93 AMUs. So, what we're trying to figure out is how much the average copper atom weighs. So we said average, equals well, the percent is a decimal. So my first percent is 69.11. So that is, move it over twice, 0.6911 times the mass of the first one, 62.93 AMUs, plus, well, the second one I know weighs 64.93 AMUs. But how am I supposed to get the percent? All they told me was the rest. Well, what do the percents have to add up to? They have to add up to 100. So if I take the 100 minus the 69.11, I get 980. I get 30.89. So that means 30.89%. Here's my other percentage. So that's 0.3089. And I push that into my calculator. 0.6911 times 62.93 plus 0.3089 times 64.93 equals. Okay, I get a whole screen full of numbers, and on tonight's homework, I want you to go to 2 decimal places. All the answers should have 2 decimal places. And my units, I got AMUs plus AMUs, that is AMUs. Actually, there's more. Okay. Now, so the average atom weighs 63.55. But we should have known that. Or we could have known that ahead of time. Because if you look up copper on the periodic table, Right underneath it, it says 63.55. Because the key says that that is the average atomic mass. That's where those decimal points came from. You know, mass numbers can't have a decimal point because you have to have a whole number of protons and neutrons. But atomic masses have those decimal points because they're averages. Think about it. When they calculate a GPA, a GPA is made up of whole numbers. If you you either get a 0, a 1, a 2, a 3, a 4, if it's an honors class, a 5, right? Those are the numbers they work with. Do you know anybody who has a perfect whole number as a GPA? I don't, and it's very rare for somebody to have a perfect whole number for a GPA. Okay? Because it's an average of whole numbers. So just like I'm putting together whole pieces here, I'm not going to get a whole number average. I'm going to do a decimal point. Okay, couple things to check. Okay, this right here, 62.93, that's really close to 63, isn't it? Because what they're talking about there is copper 63. That the mass number is really close to the atomic mass in AMUs. It's off a little bit. So 64.93, then they're talking about copper 65. Okay. Now, I got copper 63 and copper 65, but the answer is closer to 63 than 65. It's not right in the middle. It's not copper 64. Why is it closer to 63 than to 65? The same reason it was closer to 50 than 60 for the rocks. There was more of the 63 than the 65. So if you've got more of it, it's going to be close to that answer. Make sense? Okay. Sorry. So magnesium has 3 isotopes. (78.99% is magnesium-24 with the atomic mass of 23.985. 10% with magnesium-25 with an atomic mass of 24.986, and the rest with a mass of 25.983 AMUs. What's the atomic mass of magnesium? So there's 3 kinds of magnesium. What does the average magnesium weigh? That's what this question's asking. So the average equals, we said it was going to take the percent as a decimal, and the first percent I have is 0.7899 when I move it over twice. And that's times 23.985 AMUs. Plus the next one, 0.1000 times 24.986 AMUs. Plus, well, I know the third one is 25.983 AMUs, but I don't know the percentage. Well, 78.99 plus 10 is 88.99. And the rest is 25, so 100 minus 88.99 is 1011, 11.01%. That would be 0.1101. And if you type all those buttons in your calculator, and with 2 decimal places, I get 24.31 AMUs. Which shouldn't surprise me, because if I look magnesium up on the periodic table, right underneath it, it says 24.31. So notice magnesium 26 is really, really close to 26. Magnesium 25 is close to 25. Magnesium 24 is close to 24. Okay, so even though we came close to making this out of pretty close to whole numbers, we got something right in the middle. Okay, so the atomic mass is not a whole number because it's an average. And atomic mass is the decimal number on the periodic table. I mean, the key said average atomic mass, so that's what it is, the average atomic mass.